Hello, and welcome to the March webinar presentation by the Underground Construction Association Younger Members Group. My name is Colin Sessions, and I am one of the members of the UCA of SME Standing Committee for Young Members. I am joined by Anthony Bauer, the Chair, Shannon Goff, the University Outreach Chair, Everett Litton, the Membership Chair, and Demetrio Kruscalo, the Media Chair. UCA Young Members Group is a standing committee of UCA of SME that consists of professionals of all age who strive to attract and develop engineers and construction professionals under the age of 35. Each month, we put on a free webinar on various tunneling topics available to all interested parties. Before we begin this month's webinar, I have two quick announcements. Once again this year, the Young Members Group is offering a scholarship for students to attend the RETC conference in June. The scholarship is up on our website as well as the RETC website. I encourage any students who are interested in attending the conference to apply, but if you're not a student and know someone who might be, please let them know. Applications for that are due April 12th. There are also a few other scholarships available on the RETC website for students, so check those out too. Finally, those who logged into the webinar early saw an advertisement for next month's webinar. Brad Crenshaw from GEC Drilling and Grouting will be presenting on grouting applications for underground construction. More information on registering for that webinar will come out as we approach the date. Today, Jon Hurt will be presenting on precast concrete segmental lining design. Jon is the leader of ARUP's tunnel practice in the Americas and the global leader for the Tunnel Skills Network. Responsibilities for that include providing resources, training, and knowledge sharing within ARUP's tunneling community. He is a project manager and tunnel engineer with a wide range of experience in the management, design, and construction of major tunneling projects. Jon is currently the project manager for the Department of Energy's Long Baseline Neutrino Facility, Farsight project. His experience includes underground construction projects on 5 continents, including the high-speed one in London, New York's 2nd Avenue subway, and Lake Mead Intake No. 3. His other responsibilities at ARUP include coordination of the philanthropic program in the Americas. Jon graduated from the University of Cambridge with a degree in engineering. Jon, thank you for presenting for us today, and when you're ready, oh, looks like you've already shared your screen.
Yep. Hi everyone, can you hear me okay?
Yep.
I guess good. Okay, well, I'll get started. So thanks very much for this opportunity, and as Colin mentioned, my topic's going to be precast concrete segmental liners. I think Colin already went through the introduction, so I won't repeat this again. But I've been working with segmental linings for over 20 years now and seen them develop quite a lot in that time. So I guess as an overall introduction to segmental linings, just to go through some of the reasons we use them and the benefits they give us. So segmental linings allow you to place immediate support behind your tunnel boring machine. Obviously this is something in soft ground that's essential. You need to provide that immediate support there after you've excavated the ground. They also allow one-pass tunnel lining system, so you're putting in support as you tunnel, but you can also use that as the permanent support. You don't need to come and put another lining in place. You know, so that's different, say, to a rock tunnel where you can go along, you can put in some temporary support, and then you can come along, cast a lining later. A segmental lining, which you can use in either soft ground or rock applications, allows you to put in a one-pass system straight away. It also allows a relatively high-speed method of excavating your tunnel, installing a lining. One other big advantage is the quality of the concrete work that you can put into place. So the segments, as we'll see, are factory manufactured. You can have very repetitive working, high quality control, a controlled environment. So that's, you're taking away a lot of the constraints of normally working in a tunnel where you're dealing with concreting and you've got difficult environment, cramped conditions, you've got difficult logistics of getting the concrete into place. So you're delivering, you know, factory quality lining into the tunnel and then assembling it behind the TBM. And the other thing that segmentally lining your tunnel will do is give you an essentially watertight tunnel. There's never a perfect system that will absolutely cut out water, but with the gasketing system that we'll discuss that you can use in segmental lining systems, you can get a tunnel that's dry enough for the uses we need it for, whether it be transport, water conveyance, or utilities. I'll use several projects as illustrations as I go through my presentation, and the picture in the background is from Brisbane Airport Link, which I believe is the world's largest steel fiber reinforced concrete lining. So this tunnel is just over 11 meters internal diameter, and the lining has no rebar reinforcement. It's all steel fiber reinforced, and you can also see a steel section, which we'll talk about, but these are often used where a cross passage is going to be installed to provide additional support. So, you know, on the larger tunnels, these segments can get quite large that we use to build our lining. This is an image of the segments from the Brisbane Airport Link, just to give you an idea of the scale of some of this work that we're talking about. So to go through some terminology, first of all, this is an isometric of a tunnel lining, and the lining is made up of a series of rings. You can see here. The length of these rings will vary with the tunnel diameter and the TBM equipment. Generally, the larger the tunnel, the longer your ring can be, the wider your ring can be. So you may be down at about a 4-foot ring in some of the smaller tunnels, whereas you can be up at 6 feet plus in some of the larger diameter applications. So each ring is made up of a number of segments that will be assembled to form the ring, and I'll talk through some of the different geometry that we can get in the segments. But one important segment in the ring is the keystone, which is the last segment to be installed and makes up the circle. The inside lining is often referred to as the intrados, and the outside is the extrados. And then we have a series of joints between segments. We have the longitudinal joints, which run along the alignment of the tunnel. They're sometimes also called the radial joints. And then the joints at the face of the ring is known as the circumferential or circle joint. The segments are held together by fixings, either bolts or dowels, so you'll often see recesses for bolt pockets. We'll look at joints in more detail as we go through the presentation. And then we also have other fittings like grout holes or lifting sockets in the segments as well. So going from an illustration to real life, this is a photograph from the 7 line extension in New York, where after the segmental tunnel had been placed, we came along and excavated some ventilation drifts. So I thought this is a great photo that actually you can see in real life, a kind of exposed end of a ring. So again, you can see the segments, the bolt pockets, the keystone here, and then your radial or longitudinal joints running down the tunnel, and the circumferential joint on the face of the ring. And then we also have what you can clearly see here is a grouted annulus. So we'll talk about this in more detail, but as the tunnel is excavated, we do have a slightly larger diameter than the outside extrados diameter of the segments, and that is filled with grout. And you can see here between the rock and the segment, we have that grouted annulus. I've put some useful references on these slides, which I believe will be available afterwards, just talking about various different guides on design, manufacture, and erection of segments into lining. There's the French Tunneling Society, AFTES, the British Tunneling Society, and the ITA has some guidelines, among others, and there's a good paper I've referenced as well. So I said I'd talk through some of the different lining configurations, and these images are taken from the publications I mentioned, if you want to look into this in more detail. But a rectangular lining, essentially here, apart from the keystone, all the joints are 90 degrees, so it's a rectangular shape for each of the segments if you unrolled the tunnel flat. This is, I guess, how tunnel linings, segmental linings started off, and they're still very common today, especially in the very large diameter tunnels. And to show you this kind of rolled out flat, so often when we're drawing out segmental linings, it's a convenient way to show them is with as if you take the tunnel, you cut the ring and you roll it out flat so you can see the geometry configuration. So in this drawing, the constructed tunnel would be down the page. You can see a completed ring, and then another ring on top of that, and it shows you how the key segment can be inserted from the TBM side to close the ring. So just some photos of this in use. This is a tunnel, about 24-foot diameter tunnel for the high-speed rail tunnels in the UK that I worked on. This is currently the world's largest TBM tunnel. It's the subsea connection between Hong Kong Airport and the mainland that Bouygues is just finishing off. So you can see here they've used a rectangular segment. The only angled joints is when you have a key. It's a relatively large key here. Just to show you a bit more about this project, it's about 4 kilometers in length, running from mainland to the Hong Kong airport. And the section highlighted there, which is through the section of reclamation, they needed enough space for 3 traffic lanes as a climbing lane, so they used an extra large TBM, pretty much running the length of this reclamation, which is about 3/4 of a kilometer. Closer to home, there's also another very large diameter. In fact, I think the internal diameter of this tunnel is the largest, but the TBM is slightly smaller. But up in Seattle, the SR99 Alaskan Way replacement tunnel. That is, those of you that are following the news closely know that within a week should be breaking through. There's just over 200 feet remaining as of yesterday. So it's interesting to see, again, a rectangular segmental lining. This time the key is a smaller key. As segments developed, people introduced the concept of angled joints, and this brings some advantages. One is you avoid the situation where you could possibly have 4 joints aligning, which is known as a cruciform joint, and that's not good for waterproofing with the gaskets. So this helps to do that. This also brings the advantages of when you are installing the alignments, you're not, the gaskets on the joints, on the longitudinal joints, are not in contact for such a long time, and it helps to with the erection of the segments without damaging the gasket. So this is a trapezoidal lining. It's also known as a universal ring because it can be placed in many different configurations. Similar to that is a rhomboidal lining, which is very common these days. So in this case, you start off with a counter key, which gets placed first. Then you have rhomboidal segments, and you finish up with a regular key segment. And this is an isometric of a lining with the rhomboidal arrangement. So you would place the counter key first, and then the rhomboidal segments, and then the segment in the crown. And this is a photo from Lake Mead intake number 3. So it's not a great quality photo, but this was a rhomboidal segment arrangement where we had five segments plus the key. And just to talk about this project in a little more detail, this is currently the world's deepest subaqueous tunnel. The lining and the TBM were designed to handle pressures of up to 17 bar, which is 170 meter waterhead. It starts off in metamorphic rocks on the shore and heads out under the lake, and most of the drive was in sedimentary rock. So they're the main types of linings that you'll see commonly used, and I wanted to also cover a couple of other types that have specific uses. We don't see them so much these days, but they are suitable in some projects. So one of these is an expanded lining. I came across this when I was working in London 20 years ago. We were able to excavate a tunnel in the stiff London clay, and then instead of having a lining which bolted up, you could just place the segments directly against the excavated surface and then push in the keystone, which you can see in the crown here, and it would expand the lining against the excavated surfaces. So this type of tunnel lining system is appropriate if you have stiff ground that's going to stand up relatively well between excavation and placement of the lining. It's not seen so much these days. It's difficult to waterproof because you don't have the ability to compress gaskets around the outside. But it still has uses in utility tunnels and other tunnels that are in pretty impermeable situations. It also allows a very fast excavation because you're not having to do any bolting or fixing the segments together. Another type of system that also allows very fast construction is a hexagonal or a honeycomb lining. In this case, you can see the configuration, but the segments in the ring are staggered so that they kind of step half a segment as you go. There's a photo here which probably explains that better than I can. It does mean that you can be continuously advancing your TBM by pushing off the two segments on the leading side of the ring while the other segments are going into place. Again, this would be difficult to waterproof with a gasket system because it's difficult to compress the gaskets. And so again, it's most useful in ground that's pretty self-supporting, pretty impermeable. Certainly being used on some very long hydropower tunnels for inlet tunnels and water transfer tunnels where the leakage isn't quite so important. So one other aspect with the geometry of segmental linings is the use of tapering, and this allows us to steer the lining around curves. So when segmental linings were first introduced, you could go around a curve. You put in thin sheets of timber packing between the joints on the outside of the curve to help steer the tunnel lining around the curve. But with the introduction of tapered linings, you can get away from using packing and just use the lining itself. And the way this works is that one side of the tunnel lining ring is slightly longer than the other side, so that you have basically the two circumferential joint faces are not parallel. They're at a slight angle to each other. And when you put the rings together, by locating the longest side of the ring in the right place, you can steer the lining. And as this exaggerated image shows here, when you're trying to go straight, you would just alternate. So you'd have the longest length on one side and then put it 180 degrees on the following ring. But as soon as you want to go around a curve, you can start putting the longer edge on the outside of the curve. And TPMs with the guidance systems will have this information input that will allow the operators to select exactly where the longest edge of the segment goes. I think you may have noticed on earlier drawings that the segments have a number of connection points between the rings. We call these the clock positions. Depending on your segment geometry, these can vary between about 11 or and going up to 15, 16 of these per ring. So any of these clock positions you can use to align one ring to the next. So you have 16 possible ways to rotate one ring to the next, for example, if you have 16 clock positions, and that gives you 16 different locations to put the longest edge, so you can steer the lining with good accuracy. And this avoids the need for packing, which makes the joints tighter, which makes the gaskets work better, so you have a better overall lining product. So another important aspect of geometry in segments that we spend quite a bit of time on during design is the design of joints. And we're aiming here to make sure that we don't see damage when the segments are placed together and then loaded up. And we're also making sure that we can meet good tolerances. So as the photo on the left shows, we have a raised section in the middle of the segment, and then we have recesses all around that. And these recesses I like to call them a stress relief groove, is really so that if the segments are put together and they're not perfectly in a true circle, so that the joint is angled slightly rather than being completely flush, then the segments will be bearing against each other, not right on the edge of the segment, but on the edge of this raised section. And that avoids damage by having, all the load of the rings pressing together right on the inside edge of the segment. You can also see the various recesses for the bolting system, so that they're formed into the segment, so that when you put the bolts in, you have in this case, you have the socket already embedded, and you have like a slightly enlarged section that helps you guide the bolt in when you're putting it together. And then on the other side of the segment is where the bolt will come through from the inside face into a socket like this. On some projects, not so much in the US, but in other parts of the world, some designers like to provide shear keys to help with the alignment. So this is just included to give you the complete picture, that you can use a concrete shear key and that will help with the alignment. I think US practice is more to use the dowels and maybe other alignment tools that I'll talk about, instead of using the concrete, which can cause some damage. The other aspect of joint geometry, which we'll talk more about in detail, is accommodating the gasket. So the gasket is a rubber gasket that's placed all the way around the extrados side of the segment, and that has to fit in a groove that's cast into the concrete, and the dimensioning of that groove is very important to ensure watertightness. So I've been through geometry, and I'll now talk about some of the materials we use in segments. and I'll talk through these different topics: the use of reinforced concrete, the use of steel fiber reinforced concrete without or rebar, or sometimes in a hybrid with rebar solutions. I'll talk about the use of polypropylene fibers for fire resistance, how we deal with the concrete lining in sewer tunnels where we may have hydrogen sulphide attack, and I'll briefly talk about the metal segmental linings that we saw earlier in the presentation. So I mentioned one of the advantages of segments is the factory quality that we can get, and certainly this means we can get a very high quality concrete. Many of our tunnels these days have design lives of 100 or 120 years. So to achieve that, we're looking at very high quality concrete. We also rely on the concrete for watertightness. Apart from the joints, which are sealed with gaskets, the prevention of water flowing into the tunnel is also is taken by the concrete itself. So we want a very dense, impermeable and durable mix resulting from that. And so you'll often see that the specifications for precast concrete segments are higher than you would normally see for a typical site mix. One thing the manufacturers like is to have a relatively high early strength, because they want to use their molds as often as possible. So being able to take the segment out of the mold at an early age is important. So for the reinforced concrete, we would normally see prefabricated cages of the reinforcements used. This just speeds up the manufacturing process. So the design of the rebar takes into account the fact that it should be assembled as a cage and either welded or fixed, tied. And different manufacturers have different systems as to how they do this. You can range from fully automated robotic systems that will bend and weld your rebar together, which you would see on very large jobs where you're doing maybe 10 to 20 miles of the same segment, and it can go down to just hand-built cages built off frames in the manufacturer's yard if it's a relatively short job. To maintain durability with reinforced concrete, it's obviously a major concern in all concrete structures. We have to worry about cover. So one thing that does mean is some of the areas of your segments that see the highest stresses during some of the manufacturing and assembly loads, which your corners that might get damaged, don't have rebar near them due to the cover areas. But reinforced concrete cages have been used for many years. They're a very good solution. But they're increasingly, we're seeing the use of steel fiber reinforced concrete as an alternative. So the arguments for steel fiber is that there's really two main ones. One is that you can get better durability. You don't have a continuous reinforcement cage in your lining that you need to have adequate cover protection. So you can use steel fiber. It's a discontinuous kind of steel fiber matrix. So generally the durability of steel fiber concrete is considered better than concrete with a reinforcing cage. So that's one advantage. The other advantage is it simplifies your manufacturing process. So you have less labor requirements for fixing and placing the rebar. And although the material costs also come into the equation, generally it's considered to be a cost saving. The cost saving varies where you are around the world, depending on the cost of labor. One concern you often hear raised about steel fiber segments is, when you have a rough surface on the inside of the tunnel, and because this is a formed application, you get beautifully smooth segments. And people are often thinking of shotcrete linings where the fibers stick out if you use fibers, but with the formed segments you get a very good surface. At the most you might see a very slight discoloration if there's a fiber lying very close to the surface, but it's been well proven not to be a problem. One of the other advantages of steel fibers is if you do get some damage to the segmental lining after the lining is installed or during the lining installation, then the standard of repair is not quite so high, because you don't need to worry about protecting that rebar cage against future corrosion. You just need to worry about making the segment watertight. So it has been recorded as reducing the repair costs for segmental linings. Okay, polypropylene fibers. So I should mention, in terms of fiber reinforcement for the structural strength, the steel fibers have been the predominant use since this technology has been introduced, and certainly throughout my career. I think the first steel fiber tunnel I did was in 1996. So that it's a well-proven technology with steel fibers. There's certainly a lot of people looking at the use of plastic fibers these days to provide the same structural capability, and there's been some good recent papers published by ITA and others that this is certainly an area that researchers are looking into, and I expect we'll see it being used more widely in some tunnels soon. So that was plastic fibers for structural reinforcement, but polypropylene fibers, which I want to discuss now, are primarily used for protection of the lining in the case of a fire. So there was in the 90s there was a spate of tunnel fires. The store belt happened during construction, and the channel tunnel was during operation, and in both cases there was significant damage to the segmental lining. These fires can see extreme temperatures, and if you're trying to hold up cohesive ground of sand and gravels with high water pressure behind one of these segmental linings, if you're having a fire which sees a loss of section due to spalling, it could potentially be a very serious tunnel scenario. So polypropylene fibers were introduced as a way of limiting the damage you get during a fire, and they also have the advantage of minimizing explosive spalling, which when the spalling event happens during a fire, often the parts of the lining that come off are actually ejected at quite high speed, and if you did have any emergency personnel in the tunnel, that could be potential danger. To explain how these work, in normal concrete, when you expose them to these high temperatures, they're essentially the heat is trying to force the moisture to move away from the heat front, but the vapor, the moisture in the tunnel, in the segment, is trapped and it can't really move, so it basically just results in an increasing pressure, and that pressure eventually grows stronger than the tensile pressure of the concrete and causes this explosive spalling with the bits of concrete flying off into the tunnel. So the use of polypropylene fibers is believed to avoid that situation by causing a maze of interconnected capillary ducts that allows the pressure to escape. So the fibers will melt at a relatively low temperature and allow the pressure to dissipate, and so you don't have the tensile strength overcome and it minimizes damage to the segments. Just to show the difference, this was testing done on high-speed 1 tunnels in the UK that I was involved in. So you have 2 identical concrete mixes. They were tested in exactly the same way. The only difference is the segment on the right has polypropylene fibers. So you can see that there's a lot of loss of section in just the conventional concrete mix, and absolutely nothing at all in the mix with polypropylene fibers. In terms of design, there was some reduction in strength of the concrete that was exposed to the higher temperatures, so we had to consider that reduction, but we didn't have to consider the loss of section. So some of our tunnels carry raw sewage, or sewage that's diluted in CSO systems, and so we need to, in those cases, we need to do an assessment of the concentrations because we're concerned about hydrogen sulphide attack. This is where the breakdown of the material in the sewage basically forms sulfuric acid, which can attack the lining. So there's been various ways looked at doing this, and this is really to avoid the need to put in a completely independent secondary lining. But there's been ways looked at to make the segments act as an all-in-one integral liner. So you can either play around with the materials in the concrete mix itself and add some expensive additives. So that can result in a lining that can resist the attack, but the materials generally become very expensive, and so you have to weigh that up against the cost of the alternative. The alternative normally is to cast another lining inside, a cast-in-place concrete lining, and on the inside surface of that lining you would place an HDPE lining that provides resistance against the hydrogen sulphide attack. But obviously that's a whole other operation. You're placing concrete, you're placing another lining. The other way that is being looked at the moment with segments to provide a one-pass solution is to use integrated glass fiber linings within the segments. This is a solution that's patented by Heron Connect called combi segments. So you have the HDPE lining cast into the front face of the segments and going round the corner up as far as the gasket position. So any concrete surface that is exposed to the sewage is protected by this lining. In the top right here you can see the mold, you can see the back side of the HDPE. This is an agru solution here. Has the various protrusions of the fixings that will tie it into the concrete mix. We have 2 sockets here. They're used in this case to guide the vacuum lift that the TBM erector on the segments brings into place. And the other difference with this solution is that the gasket is on the inside face rather than the outside face. So you can see the gasket here, and that provides the seal against any of the hydrogen sulphide that might cause attack to the segment, stop it going down the side of the segments. These photos are from a job in Canada. It's the West Trunk sewer contract number 2, where we're using some of these segments for a relatively short length. We have 150 meters of that tunnel that needs protection, and we're currently casting the segments. Arup is working for Technicore on that. So it's pretty interesting to see this new technology being used, and the segment should be installed sometime in the fall. I did mention briefly about steel and other forms of metallic segments, and we normally use these around cross passages where we want to provide a bit of a stiffer opening, a stiffer frame around a further opening. And these can either be manufactured in steel, as you see on the right hand side here, so just welded together, or they can be a cast solution using spheroidal graphite iron, which is typical use for access chamber covers and things like that in the streets. If you have many occurrences where you need these openings, the casting may be cheaper. And these are fabricated to be the same types of sizes as the concrete segments, and they would have a facing plate put on so the TBM erector can lift them into place. Then once the tunnel is complete, you can come back and you can mine the cross passage with less support needed. So I talked about materials. We also have various fixings and that we use with our tunnels. I'll talk about gaskets in more detail. To join segments, we either have a bolted system or dowels, or a combination of both. Dowels work in the circle joint, and it's basically a press fit. You're pushing the dowel into preformed holes in the concrete lining. Once the segments are pushed together, the dowels have teeth to hold the segments together. And with bolting, you have the socket cast into one segment, and you bolt through a preformed hole in the other. Typically, you can only use bolting on the longitudinal or radial joints because the dowel geometry doesn't work, but on the circle joint, you can use either solution. Generally, dowels are faster and quicker and a better solution overall. There's also various alignment tools, so either this ball socket here, which goes around the bolting on the circle joint, or this rod, circular rod here. So they're just different ways of helping you align your segments to improve the accuracy of the build and get it as close as possible to a true circle all the time. So gaskets, these are essential part of the lining because they provide the watertightness. As I mentioned before, you have a gasket around each segment on the extruder side typically, and they sit in a groove, and the groove dimensions are very carefully calculated by the gasket manufacturers, and it's very important because the way these gaskets work is as you compress the segments together, the gaskets get compressed down. You can see they've got various holes in the gasket profile that allow it to be squashed. But essentially, it's the force of the two gaskets pressing together that creates the watertight seal. And so the geometry of the segment is very important to help that happen. So the manufacturers will, work with you during the design and manufacturing stages to make sure the gasket is the right pressure rating for your tunnel. But we have this triangle of gasket performance. If there's a gap between the segments, that tends to reduce the effectiveness of the gaskets. As you'd expect, they're not compressed against each other so hard. If you have an offset between the segments so that the gaskets aren't overlapping quite as much as the optimum position, that also reduces the water tightness. So you can see as anywhere you move in this triangle by changing your gap and your offset, the more you reduce the gap and reduce the offset, the more watertight your gasket becomes. And typically in specifications, we specify a maximum gap and a maximum offset that the gasket must perform at. And even at that gasket rating, even at those extreme positions, we require a gasket rating of double the outside pressure. Part of that 200% increase on the actual hydrostatic pressure is to allow for gasket relaxation over time. Rubber is a material that relaxes over its life, and so the 200% you get on day one, maybe after 100 years, will be down to about 140%, which is a more typical factor of safety. So all gaskets are tested, and the T joint is the most critical location. So this rig is used to test it and make sure that you hold the pressure. The other data you'll need from the manufacturer during the design process is to understand the forces needed to close the gasket gap and make sure your segment is designed to accommodate that. I'll just talk quickly through the ring design of segments. There's quite a lot of guidance, and there's a whole range of different methods ranging from continuum analysis methods where you can use spreadsheets, beam spring models, and then numerical analysis, either 2D or 3D. I think the important thing to remember with numerical analysis is, your worst design case is when you get is often when you get high overburden. That's your case that gives you the highest thrust loads in your segments. And so when you're considering what's relaxations to apply to the face, you need to really think about the worst scenarios that can happen with the TBM, including it not operating as it should. You still want your tunnel lining to stand up if you've got a ground disturbance, and that design carries through the whole alignment. So that's one critical load case, which is a high thrust case. And when you get deep tunnels like Lake Mead with very high external water pressures, that tends to be what governs the design. Often on the shallower tunnels that we would typically see from metro or subway projects, it's more likely that the segment design is governed by a high bending moment case with the low thrust. So your most critical location is probably where the tunnel is shallowest. But we would normally go along the alignment, pick out critical sections, both in terms of the different loading cases causing high thrust or high bending, and then the different ground conditions. The stiffness of the ground will impact how much loading you will see. The other important thing to consider during segment design is the manufacturing and installation cases. So often the most critical cases are actually during these cases, rather than when the segment is in a nice circular shape with balanced hoop loads in the ground. So we would consider all the load cases right from stripping through the mold, when the segments are turned, when the concrete is still relatively early strength, transporting around, and certainly when you get into some of these job sites, there's some fairly interesting ways that people maneuver segments around, and then they get lifted into the tunnel and put into place, and then there's a lot of force put on from shaft rangs. I guess one of the key areas of design is dealing with the joints, and this is where you're applying your loads to less than the full thickness of the segment, either from the shove ram pushing the TBM forward, or from on the radial joint, the hoop load in the segments. And one thing we do need to consider is bursting stresses, where you have your stresses applied over a narrow area of the segment, similar to a design of an anchorage in a post-tensioning situation. You have to look at what happens as the forces spread out in the segment and create tension. So you'll often see rebar in the segments that has ladders on the side here with some bars designed to stop that bursting effect. And there have been segment tests done to look at this bursting effect, and there's some interesting papers on projects that kind of show the types of capacities you can reach. So I'm going to very quickly talk through the manufacturing and installation process now, and hopefully have some time for questions at the end. There's various different types of manufacturing plants. This is a stationary plant, which means that the molds are kept in the same place the whole time, and you you bring the materials and the concrete to the molds. Typically these work on a 24-hour cycle, so the day shift will cast the segments. You may then cover them to allow steam curing, but you know, they have 24 hours, and then they're removed from the mold the next morning, and the process repeats itself. You can speed up the process with a carousel plant, and this is where the molds travel around the factory on a rail system, a series of stations. This is like the assembly line that you'd see in a Ford factory or something like that. So each station has its own particular job, whether it's removing the previous segment, cleaning the mold, putting in the various fixings. And the advantage with these is you get more use out of your molds. You can probably get 3 segments a day out of each mold. The molds are machined metal. These have to be built to high tolerances. We're typically talking 1 or 2 millimeters is maximum allowable tolerances on the segments. And they also have to take the strain of repeated use. If you're using this several hundred times, you want to make sure that the segment tolerances stay the same throughout. So the molds tend to have sides that can move back to allow for stripping of the segments, and then you have covers on the outsides that will help form the outside shape. In terms of concreting, so you have your mold. You have it. If you have a rebar cage, you have the cage in place. The concrete is placed, vibrated into place, and then then the outside surface is screeded and finished off. Vibration is obviously very important, as with all concrete placement, and you can either have vibrators fixed to the concrete molds themselves, or you can use external. And then the segments are cured, and what you'll often see in the carousel factories is a steam oven, so this just speeds up the process further. The segments go into the steam oven to help them gain an good early strength and improve the quality of the concrete. I mentioned lifting equipment. You just need to be aware of what your contractor's using. So maybe for a job, this was in Dominican Republic, where you may have some more interesting devices. You need to make sure your segment's designed for the single point lifts that we saw there. These vacuum lifts or side grips help to distribute the stresses very evenly. There's just a view of a vacuum lift of a segment out of a mold. So quickly go through the process of in the mold. So you're first of all cleaning the mold. You're putting in the various fittings, such as the recesses here for the shear cone. This is the concrete placement, so it's inside an insulated shed. This is like a factory condition, so you want to isolate your workers from too much noise. So the concrete work's going on behind these windows here, and this is what's going on inside there. In this case, concrete was batched for each segment, so you could control the volumes very carefully. If you're using steel fibers, this is a typical dosing machine looking down on the inside. This just feeds into the concrete batching so that you have exactly the right dosage in each batch. And this is what the steel fiber concrete looks like close up. And to give you a sense of scale, those fibers are about 2 inches or 50 millimeters long. So then the outside surface is finished, generally tamped down and then troweled. And it is important to get a smooth finish here. This affects in the TBM as the segment is pushed out. You use tail grease to maintain a seal between the segments and the TBM. And if the rougher you make this surface, the increased amount of tail grease you'll be using in your TBM. So it's smoother, the better. So you can just see them being troweled off and finished. Excuse me. Segment going into the oven. coming out the other side. And then it's time to strip the segments. So the covers and the sides are removed, and the segment is lifted out with a vacuum lift in this case. At this point, it's good to make any cosmetic repairs. As I mentioned before, the gasket grooves are important. If there's any blowholes or pinholes, it's good to seal those up because it will impact the effectiveness of the segments. I'm going a little bit fast because I want to leave time for questions. Gaskets are installed and pressed into place with the frame. And then we often build a demonstration ring at the beginning of production, and this is really to make sure that all the tolerances are working correctly and everything fits together. You obviously have to build this without gaskets, this is back on the Brisbane Airport Link job, and you can just see that everything's kind of fitting together nicely, and you would do all your checks of geometry to make sure that everything's building to the correct diameters and the gaps between the segments are all working out fine. So, and then installation in the tunnel. The segments arrive down in the tunnel on the train. They're picked up and moved to the front of the TBM. And then when they're in the front of the TBM, they're picked up by the TBM segment erector. On the lining itself, the thrust rams from the TBM are removed from the portion of the previous ring where the new segment will be placed. Obviously, the rest of the rams need to stay in place to hold the TBM and the rest of the lining in place. So you remove the shove rams, then you move up the segment erector to position the segment into the correct location. And that's the segment in location there. If dowels are being used, the dowels have been pushed into position by now. If you're using bolts, you would need to bolt up the segment. And then the thrust rams are put back on, and you repeat that process around the whole ring to give you the complete ring. Just quickly to talk through annulus grouting. As I mentioned before, we need to fill the void behind the segments. Especially in soft ground, we want to fill that void quickly and with enough pressure to minimize settlement. We can use a whole range of different types of grouts. There's some fairly inert mixes with a lot of sand and fly ash that are sometimes used, or you can use a two-component mix, which has an A and a B component, so that it basically gels within a few seconds of being placed around the lining, and provides very good support to your lining, and that's certainly has a lot of supporters. The grouting is generally placed through the tail skin of the TBM, and there's voids that allow you to pump the grout, and they come out at the back of the TBM where at the end of the tail skin. And I showed you this picture before, just a reminder of the grouted annulus, and certainly on 7 line they did a great job of having a completely filled annulus, good support to the lining. I have a few slides on segment damage. I think the underlying message here is that if you build your segmental rings with very careful attention to tolerance and getting everything as close to a circle as possible, and making sure that the circumferential face is plane, then you'll see very little problems with segment damage. But as soon as you lose control of your segment build, you'll start to see damage, whether it's due to steps in the lining or just unequal bearing of the segments. There is some useful papers and research that's been done looking at different types of damage, and I think some of the main conclusions are that you see more damage on curves. That's where you tend to lose the geometry, and you also tend to have the TBM pushing harder on one side of the segment than others. There's obviously some damage that you just can't repair, like the image on the left-hand side, and other damage that you can repair, such as superficial damage on the inside. And there's some good guidelines out there from various different tunneling societies and standard specifications on specifying exactly what repairs need to be done and what type of materials need to be used. So I've taken up nearly the full hour. Apologies for that. There's a lot more information in the Concrete for Underground Structures book that SME published a few years ago. I helped put together the chapter on segmental linings together with Jon Hurt from CSI, who is a segment manufacturer. There's also a standard spec as part of that book that might be of use. And with that, I think if there's any questions, I have time to take them now.
Yes, we do have several questions that have come in already. Thank you, Jon, for a fascinating presentation. The first question asks, is SFRC synthetic fiber or steel fiber?
So it's steel fiber. Hopefully I explain that later on after that question was asked, but yes, as I mentioned, the steel fiber has a good track record of over 20 years of use now, and the synthetic fibers are certainly being looked at and researched at the moment, and I think a few trial cases have been used in tunnels as well. So there's certainly, synthetic is certainly an area of development that's being looked at.
Thank you. The next question is, and I might have to read this twice, what do you think about the use of specialty admixtures in precast segments? For instance, corrosion inhibitors, antimicrobial admixtures, crystalline capillary waterproofing admixtures. Would you like me to read it again?
No, I understand the question, and I think I mean, all of those have their place, and typically we will work with our materials experts to look at the specific situations. I think in many cases we can get a good durable concrete mix with a good design life, 120-year design life, by using a fairly conventional concrete mix. Maybe you have to look at things like microsilica to improve the permeability characteristics. But I know that there have been various projects that have been used, and I think certainly in the sewer tunnels, there's additives that can reduce the concrete attack, and so that's definitely a viable alternative when you're looking at these projects. But yeah, certainly something you need to work through with the material specialists, and it often comes down to cost and performance. What's the best way of getting the performance you need in terms of cost? So a lot of the additives are very expensive, and there's other ways to achieve it.
Great, thank you. And we do have very number of our attendees are remaining, so we're going to continue to record and ask questions of you. The next one is, can you talk about various packing material, for instance, plywood versus asphalt versus no packing material?
Okay, so I think the packing these days really is not really needed for packing in the sense we used to have it in the olden days, which was when you want to pack out the joint to help you go around a corner. So we do sometimes use materials on the joint surfaces, and the reason for that now is just to stress out, eliminate any high points where you might get stress concentrations. And personally, I prefer the bituminous materials, but I know timber works just as well. It tends to be thicker. I think in most cases unless you have a very unique situation, the concrete to concrete contact works fine. But it's something you need to consider during the design when you're looking at the actual stress situation, and also when you're considering your manufacturing tolerances as well.
Thank you. We have time for maybe one or two more. The next question is, why no corrosion protection required for SFRC?
So the reason is that as opposed to a rebar cage, where the rebar cage tends to be continuous, and you can, if you get the cage exposed in one area, then it can spread down the cage. The fibers are discontinuous. So in the event you did have one fiber that was exposed, the rest of the fibers in the mix would still be protected.
And we have time for one more question. Do the dowels on the circumferential, yes, on the circumferential joint mount perpendicular to the tapered ring face or parallel to the ring longitudinal axis?
You know, that's a very good question. I would think they have to mount perpendicular to the tunnel, or aligned with the tunnel axis, the tunnel center line. But I think there's probably enough. I mean, the tapers we're talking about are relatively small angles, and so there's probably enough flexibility. But I would have to go and look at some details to see for sure.
Terrific. Thank you again, Jon, for this wonderful presentation. I would invite all of our attendees whose questions were not read on the air to go ahead and contact Jon, and the phone number and the email that are up on your screen. And I'd like to remind all the attendees and the registrants that this webinar will be rendered and posted on the Young Members website within 48 hours. Jon, would you have any final comments for our audience?
Nothing in particular. I mean, yes, anyone that wants to contact me, please drop me an email and I'll do my best to answer your questions. But thank you very much for listening.
Thank you, everyone. This ends today's recording. Have a great day.